Riemann sum and the definite integral. In this section, we're assuming that we're dealing with a continuous positive function. So you have a function f of x. And let's say this function is positive from when x is equal a to when x is equal b. So within the interval from a to b, the function f of x is positive, meaning if you graph it, the curve is going to be above the x-axis. Okay. Now, the problem that we're trying to solve here is how can we find this area under the curve, this area, the area of this region, the region that is trapped under the curve above the x-axis and between these two vertical lines. That is the problem we're going to address in this section. It's not a regular form like a, for example, a triangle or a rectangle or a square, so that we have a formula for that and we can use the formula to find that area. Yes, so this area, because of this curve here, it's not a regular geometric shape. So what we try to do, and the method that was used in order to solve this problem in math, was to create a partition of the interval from a to b, and a regular partition. A regular partition means that each part is going to be exactly the same length. So I'm going to divide this length from a to b into, let's say, 4 partitions. And this is called a regular partition because each part has the same size as the other parts. And I'm going to give each point here a name. So let's say A is the same as x0. This is x1, this is x2, this is x3, and B is going to be the same as x4. So actually x0 is going to be this length from the origin until A. x1 would be this length from the origin until x1. x2 is going to be this length, because this is the real number line. This is the x-axis and this is the y-axis. So here I have a partition with four parts. So the next thing that we can do is we can find f of x1, which is going to be here, f of x2, which is going to be here, f of x3, which is going to be here, and finally f of x4, which is going to be here. Then we can create a rectangle like this. And this rectangle is going to have a base that is of this size and a height that is of size f of x1. So the base of this rectangle is going to be, I'm going to call the base delta x. Yes, it's going to be exactly the distance between a and b, so b minus a, divided by 4. That would be the base of this rectangle. I just found the distance from a to b, which is b minus a, and divided that by the number of rectangles that I have, or by the number of partitions that I have. That would be this length. And the height of this rectangle is going to be f of x1. Then I do the same thing here. I create another rectangle of the same base, but this time the height is going to be f of x2. Then another rectangle of the base delta x, and the height is going to be f of x3. And finally, I'm going to create a rectangle with the base, the same base, delta x, but this time the height is going to be f of x4. Yes. Now, if I add up the areas of these rectangles, and it's very easy to figure out what the area of a rectangle is, because it's just the base of the rectangles times the height of the rectangle. I'm going to get this. I'm going to get f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x. Basically, this is the area of the first rectangle. This one is the area of the second rectangle, the third rectangle, and this is the area of the last rectangle. And add them up, I'm going to get the sum of the areas of this rectangle, which is not going to be the same as the area under the curve that I was originally looking for, but you agree that it's an approximation for that. This sum is called a Riemann sum. It's called a right endpoint Riemann sum because for the height of the rectangle, I'm using the right endpoint of each one of these segments. So in this segment, I'm using the right endpoint. I calculate f of x1 for the height of the rectangle. For the next segment, the same, I'm using the right endpoint. And then for this segment, I'm also using the right endpoint of the segment. So this is called a right endpoint Riemann sum. So I don't have the area yet, but what I have is an approximation for that area. The question arises, how can I improve that approximation? Because whenever you have an approximation for a quantity that you want to measure, if you have a method of approximating that, the question is, how can you improve that method? How can you get a better approximation? And I hope you all agree that in order to get a better approximation in this situation, I have to increase the number of rectangles. If I have a larger number of rectangles, I will have thinner rectangles, and then those rectangles will fit better inside this area. And then I will have a better approximation. Now, how can I get the best approximation, or actually, how can I get the exact value? I need to increase the number of rectangles into infinity. So if I have infinitely many rectangles, then the approximation becomes actually exact. So this is the idea behind the Riemann sum. And here's the definition for that. This is the definition of a definite integral. This area here that I was talking about, so I'm talking about the area under the curve, the area that I was trying to figure out. Yes, this is denoted as integral with the bounds from a to b of f of x dx. So notice that there is a big difference between the integrals that you have seen so far, which were antiderivatives, and this here, because this is an area. So far you have seen this. For example, something like this, and we used antiderivative formulas and the substitutions so far to find the antiderivative of this function. So you remember what this is. This is the family of antiderivatives of f of x. So it's a family of functions in the form, let's say, uppercase f of x plus c, where if I take the derivative of uppercase f, I'm going to get the lowercase f. So but when you see this, it's called an indefinite integral, because it has no bounds. There is no number a and b here. There is no bounds here. And what this is a family of functions, so that the derivative of those functions would be lowercase f of x. But this new thing that we learned today is a totally different thing. It's actually this area. It's not a function. It's just a number. Integral from a to b of f of x dx. And you might ask, okay, so what's the relationship? Why are we using almost the same notation for two very different things? We will learn about that next class when I cover the fundamental theorem of calculus. But for now, just have this in mind, that what you have here is called a definite integral. compared to this one, which is an indefinite integral. This is a definite integral, and by nature, it's just a real number. It's an area of this function under this function. So this is the function f of x above the x-axis, and between the two lines x equals a and x equals b.
Sir,
and how do we? Yeah, question.
So like we know it's definite because there's the a and the b on the.
Yes.
Okay.
If the bounds are there, it's called a definite integral. If the bounds are not there, it's an indefinite integral.
Okay.
If there are no bounds like this, then it's a family of functions, all the antiderivatives of lowercase f. But if the bounds are there, it's not a function anymore. It's a number. It's a real number because it's the area under the function f of x above the x-axis and between the two vertical lines a and b. You're good?
Yeah, thank you.
And the method we find this area is that you, as I showed you, you're going to use a method called the Riemann sum. You have to partition this interval from a to b into a regular partition of n subintervals, create those rectangles. For the height of those rectangles, you're going to use f of x1, f of x2, f of x3, and so on. And then by increasing the number of the rectangles, you can improve your approximation. So if I want to just write that Riemann sum using n, I'm going to have something like this. F of x1 times delta x, that would be the area of this first rectangle. Then f of x2 times delta x, that's going to be the area of this second rectangle. And all the way to the last one, f of xn delta x, that would be the area of this last rectangle here. And now this is an approximation. This is an approximation for the area. However, if n increases to infinity, if I take the limit of this as n approaches infinity, then I get the area, which I denote using this notation. The definite integral from a to b of f of x dx. And hence you have this definition here. A definition of definite integral: if f is a continuous function defined on a closed interval from a to b, and if a to b is divided into n equal subintervals, each one will have a length of delta x, b minus a divided by n, and the formula for each xi or xk is going to be a plus k delta x. Why is that? Because, for example, x0 is going to be the same as a. Then x1 is going to be this length plus 1 delta x. x2 is going to be a plus 1, 2 delta x's. Then x3 is going to be a plus 1, 2, 3 delta x's, and so on. So the formula for each delta, for each xk is going to be a plus k times delta x's. This is the right endpoint of the subinterval k. And then the definite integral is going to be this: the limit as n approaches infinity of the sum of the fi delta x as n approaches infinity. That would be the area. So before I give you some numerical examples, I want to talk about this notation that I highlighted here, the summation notation. So we said that if I have f of x1 times delta x plus f of x2 times delta x, all the way to the last one, f of x n times delta x. And I take the limit of this as n approaches infinity. That's as if I'm increasing the number of rectangles. Then this approximation becomes exact, and I will have the area under the curve. Now, as you can see, this is very cumbersome. It's very long. And in math, we don't like that. We like very, very precise shorthand notations. So the notation that we are using for this is called a summation. A summation notation. So what is that? It's like this. Let's say we have sigma, for example, xi, I from 1 to 5. What do we mean by this? Summation of xi, I from 1 to 5. I is called an index, and it begins at 1, it ends at 5. So this is actually x1 plus x2 all the way to x5. So rather than writing this long expression, we are using a shorthand notation. Another example, you may have something like this. Let's say sigma a times bi, I from 1 to 10. What do we mean by this? We mean a b1 plus a times b2 plus a times b3 all the way to a times b10. Another notation, another example. Let's say you have sigma xi, or I can use k for the index. I can use k or I. Yk, k from, let's say, 3 to 100. What do I mean by that? This is a notation for k. It begins at 3, ends at 100. So it's going to be x3 plus y3. That's the first term. Then k becomes 4. I have x4 plus y4. And then I will have the same thing all the way up to the last term, which is when k is 100. I get x 100 plus y 100. So rather than writing something like this, I'm going to use this shorthand notation, which is called the sigma notation. So I can say that this is actually limit as n approaches infinity of, rather than writing this, I write sigma f of xk times delta x, where k changes from 1 up to n. It goes from 1, then 2, all the way up to n. So do we understand this definition now?
Yes.
So in order to find this area, actually, we need to be able to write this in terms of n. After we are able to write this in terms of n, we can take the limit of that expression in terms of n and find the area. So before going there, before I show you some examples, I'm gonna talk about some of the properties of this summation notation, which are here in the appendix. So first of all, imagine you have sigma 1 k from, let's say, 1 to 10. What does that mean? That is actually 1 plus 1 all the way 1 10 times. So you're adding 1 to itself 10 times. So this is going to be simply 10. Or generally, if you have sigma k from 1 to, let's say, whatever, let's say uppercase M, of 1, that's going to be exactly M. What if I have something like this? I have sigma k from 1 to 10 of 5. What is that? That's going to be 5 plus 5, and you're adding 5 to itself 10 times because this is going to have 10 terms. And that's going to be exactly 550, 5 times 10. So generally, if I have sigma k from 1 to n of any constant c, the answer is going to be c times n, or n times c. So that's the first formula here. So this simply means that you're adding the constant c to itself n times, so you're going to get n times c. Next one is, if you have a constant c, you can move that constant c out of, you can move it out of the sigma notation, which is basically the factoring property or the distributive property of sum. So for example, if you have sigma k from 1 to n of c a k, this is like having c a1 plus c a2 all the way to c a n. Yes, so of course you can factor out the c, and if you factor out the c, you're going to get c times sigma a k, k from 1 to n, because this is actually the sigma. The next thing that you have here, the next property, is basically the commutative property of sum. Because if you have sigma ak plus bk, k from 1 to n, then this is a1 plus b1 all the way to an plus bn. But you know that it doesn't matter in which order you add up numbers. So you can actually add up all the a's first, and then add up all the b's, then add these two together. Yes, but if you look at this one, the first one is actually sigma ak, and the second one is sigma bk, and in both cases k goes from 1 to n. So it's as if you have a sigma like this, you can distribute it. Same thing is true if you have a minus, for the same reason. Yes, so if you have, the first one is a minus b, then all the way to an minus bn, you can first add up all the a's and then add up all the b's, and you do all the a's minus all the b's, you get this. Do we understand these properties of sigma? Any questions? Okay, now the next thing that you need to know is this. I'm going to add this formula to that. If you have sigma 1, k from 1 to n, that's going to be exactly n, because that's, you're adding 1 to itself n times. If you have sigma k, k from 1 to n, that is, if you have 1 plus 2 plus 3 plus 4 all the way to n, then you can easily prove, doing some algebra, that this is going to be n times n plus 1 over 2. So for example, if I have sigma k, k from 1 to 10, that's going to be 10 times 9 over 2, that's going to be 90 over 2, that's going to be 45. So if I just do 1 plus 2 plus 3 all the way to 10, I'm going to get 45. The next formula, and these three formulas, I'm not 100% sure. I know they are provided in Cal 2 Science, but in your course, I am I need to check the one of the final exams, but I'm pretty sure that these formulas will be covered in the final exam and will be provided in the final exam. So you don't need to memorize them. If you have sigma k squared, k from 1 to n, that is if you have 1 squared plus 2 squared plus 3 squared all the way to n squared. The formula is going to be n times n plus 1 times n plus 2 over 6. And finally, if you have sigma k to the power of 3, k from 1 to n, that is you have 1 to the power of 3 plus 2 to the power of 3 all the way to n to the power of 3, the formula is just like this one to the power of 2. So it's n times n plus 1 over 2, just like this one, the whole thing to the power of 2. So you get n squared over n plus 1 squared over 2 to the power of 2, which is 4. So do we understand the sigma notation? Any questions? Now let's find some areas using the Riemann sum technique. So imagine that we want to find this area. Let me just show you the area. The function is f of x is 2x squared plus 3. And if you look at the two bounds, the bounds are 0 and 4. So if I want to graph the area, let me use a graphing tool, Desmos. Desmos is a very good graphing tool. I just want to show you the function. 2x to the power of 2 plus 3 plus 3. So that's the function. And the two vertical bars are x equals 0 and x equals 4. So x equals 0, which is the y-axis, and x equals 4, which is this line here, the green one. Okay. So this is the area that we are trying to figure out. So this area under the red curve above the x-axis and between the two vertical lines, the blue line and the green line. This is the area that we are trying to figure out. Okay. So what do we have to do? We have to partition the interval from 0 to 4. We're going to use this formula. First, we need to figure out what the sum of from k from 1 to n of f of xk delta x is going to be. That's going to be an expression. That's going to be an expression in terms of n. Yes, and then we take the limit of that expression as n approaches infinity, and we will be done. So these are the steps. So first write this, simplify it. That will be an expression in terms of n. It will have only n in it, no other variable. And then we take the limit of that as n approaches infinity, because we're going to use this formula that the integral from a to b of f of x dx is going to be limit as n approaches infinity of sigma k from 1 to n of f of x k times delta x. We're going to use the formula we just learned. I mean this formula. You good? Okay. So the first thing I need to do is to find my delta x. Delta x by formula, it's b minus a over n. and in this case, f of x is 2x squared plus 3. A is 0 and B is 4. So A is the lower bound and B is the upper bound. The lower bound is 0 and the upper bound is 4. So first I need to find the delta x. Delta x is going to be 4 minus 0 over n. So it's going to be 4 over n. You're good so far? Now we have sigma f of xk times delta x that we need to simplify and write it as an expression as an expression which has n in it only. So this is going to be sigma k from 1 to n of f of xk. Yes, what is xk? Xk also has a formula. Xk is a plus k times delta x. Yes, so this is also here in the definition. Yes, xk is a plus k delta x. And again, the reason is that in order to, for example, get x1, you need to go to a and then add 1 delta x. In order to go to x2, you need to go to a and then add 1, 2 delta x's. In order to go to x3, you need to go to a from 0 to a, and then you need to add 1, 2, 3 delta x's. So basically that's the formula. And in this particular problem, it's going to be a, which is 0, plus k times delta x, but delta x is 4 over n. There's going to be 4k over n. So this becomes f of 4k over n times delta x, which is 4 over n. Now, what is f of 4k over n? We have f of x. So I can just replace that x over there with 4k over n. I'm going to get sigma k from 1 to n of, I'm going to replace x with this. Get 2 times 4k over n squared plus 3. So this part here is f of 4k over n times 4 over n. Which is going to be sigma k from 1 to n of, okay, this is going to be 16. 16 times 2, 32 k squared over n squared plus 3 times 4 over n. So I just rose this to power of 2. 4 to the power of 2 is 16. 16 times 2 is 32. K to the power of 2 is k squared. N to the power of 2 is n squared plus 3 over times 4 over n. And next, I'm going to distribute this. I'm going to get sigma k from 1 to n of, if I do 4 times 32, I get 120, 128. I get 128 k squared over, if I multiply the n and the n to the power of 2, I get n to the power of 3, plus multiplying these two, I get 12 over n. You're good so far? Any questions? Okay, so let me keep this. Now it's time to use those properties and the formulas in the appendix. So this is going to be, I'm now using those properties because, for example, this one, it's like you can distribute the sigma, it's going to be sigma this term plus sigma this term. So I can write this as sigma 128 k squared over n cubed plus sigma 12 over n. Again, I'm using the properties of sigma. We know that if I have a constant like 128 here or n to the power of 3 here, I can move it out of the sigma. So notice that this sigma, the index in this sigma is k. It goes from k equal 1 to k equal n. So n to the power of 3 is going to be a constant. It doesn't change from term to term. The thing that changes is the k squared. N to the power of 3 does not change. So this is like having 128 over n to the power of 3 times sigma k squared plus 12 over n sigma times 1. K from 1 to n, k from 1 to n. That is 128 can be moved out of the sigma. N to the power of 3 can also be moved out of the sigma. 12 over n, both of them can be moved out of the sigma because they do not depend on k. They are constant as far as k is concerned. They do not depend on k. And for this, we have a formula, right? The formula is 128 over n to the power of 3. Now, this can be replaced by, I'm going to show you the formula again, n times n plus 1 times 2n plus 1 over 6. This. N times n plus 1 times 2n plus 1 over 6 plus 12 over n times, what is this? This is just 1 plus 1 plus 1 plus 1 n times. So this is simply n. Let's simplify this a little bit. 126 is 126 divisible, 28 divisible by 6. No. But both of them are divisible by 2. I'm going to get 128 divided by 2. I get 64. Get 64 over 3. I'm just simplifying this. N to the power of 2, m plus 1 times 2n plus 1. So this n and the one of the n's here cancel out. And then 128 divided by 2 is 64. 6 divided by 2 is 3. And the last one is just n cancels, and I get 12. You good? So now I need to take the limit of this as n approaches infinity. So that's my next step. That's going to be, I can write it like this. I can say this is limit of 64 over 3 times n plus 1 over n times 2n plus 1 over n plus 12 as n approaches infinity. I'm going to show you later, but trust me on this. The limit of n plus 1 over n as n approaches infinity is going to be 1. And the limit of 2n plus 1 over n as n approaches infinity is going to be 2. So this is going to be 2 times 164, that's 128 over 3 plus, and this is a constant, the limit does not depend on n, plus 12. So the final answer is going to be 128 divided by 3 plus 12, which is going to be, if you do the calculations, I use the calculator here, 164 over 3. And that's the area of the region I just showed you over here. It's the area of this region. Let me just check my answer and make sure that I did the calculations correctly. Example 1, 164 over 3. That's good. Okay, so I want to show you how these limits work. So I said that the limit of n plus 1 over n as n approaches infinity is going to be 1. Why is that? If you remember, we had limits like this last semester, x plus 1 over x as x approaches infinity. And what we did over there was we could divide the numerator and the denominator by x. This is going to be limit of x plus 1 over x over x over x. As x approaches infinity, this is going to be limit of 1 plus 1 over x over 1 as x approaches infinity. So this part here, as x approaches infinity, is going to be 0. Because you have numerator 1 is a constant and the denominator goes to infinity, so the whole thing is going to decrease to 0. So you get 1 over 1, which is 1. Another method that you may have remembered from last semester was something called the dominant term technique. The dominant term technique says that this limit is going to be as long as x approaches infinity. This cannot be used for any limit. Only the case when n approaches infinity or minus infinity, you can say the dominant term on top is x and at the bottom is also x. So this is 1. Or for the second one, when I had 2n plus 1 over n as n approaches infinity, using the dominant term, you can say, okay, so the dominant term on top is 2n and the dominant term at the bottom is n. So this is going to be simply 2. So that's why these limits, the limit of this part here is going to be 1, and the limit of this part is going to be 2. There is another way of reaching the same conclusion. If you have limit of n plus 1 over n as n approaches infinity, you can write that as limit of 1 plus 1 over n as n approaches infinity. And now it's clear that this part is going to go to 0, so you get 1. Or if you have the limit of 2n plus 1 over n as n approaches infinity, you can write this as limit of 2 plus 1 over n, because this over this is just 2, and this over this is 1 over n. As n approaches infinity, you get 2. So that's why this part is going to, the limit of this part is going to be 1, and the limit of this part is going to be 2. You do the calculations, you get the answer. Okay. Any questions about example 1? Let's do another one similar to this before going to example 2. So imagine I'm trying to figure this out. From 0 to 5 of 3x squared plus 1 dx. Yes. What is this? This is the area under the function f of x is 3x squared plus 1. Above the x-axis and between the lines x equals 0 and x equals 5. So in other words, a is 0 and b is 5. I'm trying to figure out that area using the Riemann method. So this is the formula, limit of the sum f of xk times delta x, k from 1 to infinity. Sorry, from 1 to n, but n approaches infinity. I find delta x first. Delta x is b minus a over n. In this case, it's going to be 5 minus 0 over n, so 5 over n. Then I find xk. Xk is a plus k delta x, so it's going to be 0 plus k times 5 over n. So it's going to be 5k over n. So I need to first write this part in terms of n, and then take the limit of that as n approaches infinity. So I'm going to have sigma f of this, f of 5k over n times delta x, which is 5 over n. Using the function, I get 3 times 5k over n squared plus 1 times 5 over n. So what I did here is that I replaced the x in the function. I replaced the x in the function with whatever I have inside the braces here, the 5k over n. So this is going to be sigma k from 1 to n of, this is going to be 25. 5 to the power of 2 is 25. 25 times 3 is 75. I get 75 k squared over n squared plus 1 times 5 over n. And if I distribute, I get 5 times 75 over n to the power of 3. Let's see, if I do 5 times 75, I get 375 k squared plus this times 1 is 5 over n. Any questions so far? So from here on is using the properties of sum. So that sum is going to be 375 over n cubed sigma k squared plus 5 over n sigma 1. This part here can be replaced with n times n plus 1 times 2n plus 1 over 6. And this here is going to be replaced with n. So if I simplify that, I get 375 times n plus 1 times 2n plus 1 over 6 times n to the power of 2, because n cancels one of the n's here. And here I get 5. And then I take the limit of this as n approaches infinity. That limit is going to be 375 over 6 times the limit of n plus 1 over n times 2n plus 1 over n plus the limit of this part is going to be just 5 because it does not depend on n. The limit of this is going to be 1. The limit of this is going to be 2. So I'm going to be left with, this 2 actually cancels the 6 here. I get 3. It's going to be 375 over 3 plus 5. And if I use the calculator for that, 375 divided by 3 plus 5 You get exactly 130. Is this clear? Any questions? Do you know how to do a sum of some fractions using a calculator, using this calculator? You're going to use this button here. So this is for the fraction bar. So for example, if you want to do something like this calculation that I just did, something like this, you would do 375 over using this button, 3 and then plus 5 gives you the answer. Yes, questions?
I was just curious about how you got from the 6 to the 3.
This part here is going to be 2. 1 times 2 is going to be 2.
Mm-hmm.
And then if you divide 2 by 2, you get 1. Divide 6 by 2, you get 3. I simplified.
Okay, thank you.
No problem. Okay, let's look at the next example. So that was example 1. You have all the example here, so every detail that I explained is also here. Let's do this one. Example 2. You're trying to figure out this area. The area under this curve above the x-axis and between the lines x equals 2 and x equals 5. In other words, A is 2 and B is 5. Same story. You have to find first what delta x is. It's going to be b minus a over n. In this case, 5 minus 2 over n. That's going to be 3 over n. Then you need to figure out what xk is. Xk, the formula is a plus k times delta x. What is a? 2 plus k times delta x, 3 over n. That's going to be 2 plus 3k over n. We're good so far? Then you need to simplify the expression sigma f of x k times delta x and write it in terms of n. After that, you will have to take the limit of this as n approaches infinity. So this is going to be sigma f of 2 plus 3k over n times delta x, which is 3 over n. Let's expand that. If I plug in this into the original function, notice that the original function f of x is 8x minus x squared. If I replace this into that function, I get 8 times 2 plus 3k over n minus 2 plus 3k over n squared, yes, times 3 over n. You good? Okay. So what I'm going to do for this one is I'm going to move this 3 over n outside the sigma, because don't forget n is a constant so far, because this depends only on k. So I'm going to write that as 3 over n sigma. If I multiply these two, what do I get? I get 16 plus, multiply these two, I get 24k over n minus. Now, raising this to the power of 2, I'm going to use a plus b squared is a squared plus 2ab plus b squared. So what do I get? I open a brace here for that one. 2 to the power of 2 is 4 plus 2 times this times this. That's going to be 12k over n. And finally, plus the last one to the power of 2, I get 9k squared over n squared. Very good. I hope I did not make any mistakes so far. 16 plus 24k over n minus 4, 12k over n, and 9k squared over n squared. Okay. I'm going to continue. At this point, I have to begin using the properties of sigma. That's 3 over n sigma. Let's just simplify here inside this a little bit. I have 16 here, and I have a minus 4 here. That gives me 12. I have a 24k over n, and I have a minus 12k over n. That gives me plus 12k over n. And finally, I have a minus 9k squared over n squared, which is going to be 3 over n times 12 times sigma 1 plus 12 over n times sigma k minus 9 over n squared times sigma k squared. So I distributed this sigma. I get 12 sigma, which is the same thing as 12 sigma 1. And then I get sigma this. The 12 over n can move out of the sigma. I get sigma k. And then I have sigma this term, but the 9 and the n squared can move out of the sigma. It goes here. Now this, I have a formula for this. I also have a formula for this. And this is simply going to be n, because I'm adding 1 to itself n times. So 3 over n is going to be 12n plus 12 over n. This part is n plus 1 over 2 minus 9 over n squared times. This part is n times n plus 1 times 2n plus 1 over 6. Let's simplify that. If I multiply these two, I get 36. This n cancels this n. I get plus 3 over 2, and there's also 12 here, so it's going to be 36 over 2. 36 over 2 times n plus 1 over n minus, let's see, here I have a 9 times 3, that's 27 over 6. I have this n here, which cancels this n. So write it down here. Minus 27 over 6 times. Okay, let's see what happens to the n's. This n cancels this n. I'm left with n plus 2 on top. I'm left with 2n plus 1 on top, and I'm left with n squared at the bottom. Just want to make sure that I did not make any mistake with the n's. These two n cancel, so I have n plus 1 on top and n at the bottom. With these ones, I can say that this n at the bottom and this n on top cancel out. and I'm left with this times this over n squared. In terms of the numbers, I have 3 times 9, which is 27 over 6. Okay, good. Now, this is the sigma. I have to take the limit of this as n approaches infinity. And you all know what's going to happen. This one, as n approaches infinity, is going to be 1. And this part here, as n approaches infinity, is going to be 2. So this is going to turn out to be 36 plus 36 over 2 minus 2 times 27 over 6. So 36, and then 36 over 2 is 18, and then the minus, that last part is going to be 2 times 27 over 6. Yes, it's going to be 9. That's correct. And if I do all these calculations, I'm going to get 45. Any questions? It's a kind of an algorithm, yes? First, you have to find the delta x, which is going to be b minus a over n. Then you need to figure out what xk is. There's a formula for that. That's a plus k times delta x. Then you find what your f of x k is. You just plug in your xk into f of x, and you simplify that. So I think this is better than what I did, because I was messing with sigmas a lot, but this is a better method, because first you calculate what f of xk is, and you simplify this. If you simplify it, expand this, and then simplify it, you get this. Now, this part, f of xk times delta x, is going to be this. You multiply them, you distribute the 3 over n, multiply by every term, you get this. And at this point, you can apply the sigma and use the properties of the sigma. This part here can be replaced with n times n plus 1 times 2n plus 1 over 6. This can be replaced with n times n plus 1 over 2. And this can be replaced with only n. And last step, after you have simplified, you have to take the limit of this expression as n approaches infinity to get the answer.